I would like to start with a little reminder of the concept of classical information that we discussed last time. Here you see again the setup that is used to define the classical information. You have two communication partners. Commonly these are, or traditionally these are Alice and Bob. And Alice performs a random experiment, actually performs several trials, and she wants to encode the sequence of results of her random experiment and send these results to Bob. And she's constrained to encode the results of her random experiments in bits. So she has to send a classical bit string to Bob, who then decodes the bit string and reconstructs the sequence of results of Alice's experiments. And we discussed last time that when you assume optimal encoding, so you want to make the bit string as short as possible, then and in the limit of very many trials, then on average the minimum number of bits that you need to encode the result of a single trial of the random experiment is given by Shannon's entropy. And in the box below you see the formula for the Shannon entropy. It depends on the probability distribution for that random experiment and is given by the formula below. Then I would like to discuss some key properties of this Shannon entropy. You see on top, once again, the formula for the Shannon entropy, and I would like to focus on three key properties. The first property is the fact that the Shannon entropy is never negative. It's always greater than or equal to 0. This is perfectly plausible. If it was any different, then there would be something wrong with the definition, because the length of the bit string that Alice has to send is never negative. There's a second part to that statement which is a little bit stronger, namely that the Shannon entropy vanishes if and only if the outcome of the random experiment is certain. And that is the case if one particular outcome occurs with probability 1 and all the other outcomes occur with probability 0. That's of course also perfectly plausible, because we said that Bob knows in advance the probability distribution of Alice's random experiment. So if he also knows that the outcome is certain, then he already knows the sequence of results and Alice doesn't have to send any bits to him. The second property states that it doesn't matter if we relabel the outcomes of the random experiment. So the pi, the symbol here, stands for a permutation. So let's think of rolling a die, and you just relabel the spots. So what previously used to be a side with 2 spots, you define as the new side with 3 spots, and so on. So you just exchange the labels of the outcomes of your random experiment, and such a relabeling has no influence on the number of bits that Alice has to send. So this is the permutation invariance. And the third property, that is, I think, the most interesting and the least trivial of these three, and that is the fact that the Shannon entropy is additive in the following sense. consider a combined experiment where Alice performs two kinds of experiments in parallel. So think of rolling a die and flipping a coin or some other random experiment. And then she wants to send to Bob the information about the outcomes of this combined experiment. And if the two experiments have nothing to do with each other, they're perfectly independent, then the amount of information, or the number of bits on average that she has to send, is just the sum of the requisite number of bits for each experiment. Yeah? So certain number of bits to convey the result of the die roll, and another number of bits to convey the result of the coin flip or some other experiment. Yeah? And you just add them up. It gets a little bit more complicated if the two random experiments are correlated. So you can invent sort of weird experiments, but let's say you have two dice, and maybe the dice are magnetic. There's this magnet hidden in the dice, and you roll one, and then you roll the other next to it, and then the outcome of the second die roll is somehow influenced by the outcome of the first. How it's on the table, that has an impact on the result of the second die roll. So they are correlated, they are no longer independent. This means specifically that the outcome of one random experiment can influence the probability distribution of the second experiment. Yeah? You have to use conditional probabilities. So let's say the first random experiment, let's call it A, gave a certain result, AI. And then for the second random experiment, B, you have a conditional probability distribution, rho or P, K, given the outcome AI of the first experiment. So these are conditional probabilities, and they can vary depending on the outcome of the first experiment. Then you can, then it's no longer obvious if so, in which way the entropy is additive. It turns out it is still additive if you define the two terms on the right-hand side carefully. So what you see here in this equation is on the left the Shannon entropy of the combined experiment, so the number of bits on average that you have to send to communicate the result of both experiments. On the right-hand side you have S of rho A, and that's as before. That's the entropy of the first experiment, A. And then the second term, that's called the conditional entropy. That's the entropy conditioned on the outcome of A. Yeah, and also you see it has a slightly different notation, and it's defined in the following way. It's a weighted average and of entropies, and you see the argument of the entropy in this sum, that's rho B given AI. So this is the conditional probability distribution of the experiment B given a specific outcome AI. And with this conditional with these conditional probabilities, you get a certain entropy. And then you take the weighted average over all possible outcomes of A. And this gives you the so-called conditional entropy of B given the outcome of A. So that is in a way the expected number or the average number of bits that you need in order to encode the result of experiment B, given that you know the outcome, whatever it is, of experiment A. Yeah, so with this qualification, you still have additivity, even if the two random experiments are not independent of each other. This conditional entropy, that is never greater than the entropy of experiment B when you don't know the outcome of A. Yeah, so when you have correlations, then this means that the outcome of A already tells you something about the expected outcome of B. So you will need less bits to encode the result of B if you already know the result of A, because this already tells you a little bit about the outcome of B, and so the remaining ignorance about the outcome of B, that's this conditional entropy that I just showed you. That can only be smaller than the ordinary entropy of experiment B, but it cannot be larger. It cannot be that when you learn the outcome of A, that suddenly you know less about the outcome of B. Yeah? So in this additivity formula on the right hand side, the conditional entropy of B given A is smaller than or at most equal to the ordinary entropy associated with the experiment B. And this implies in the next line this inequality. So no matter if you have correlations or not, this inequality is always holds. Now it turns out, and I'm telling you this without proof, that these three properties already specify the Shannon entropy uniquely up to a positive multiplicative constant. Yeah, so any information measure that you can think of and of which you demand that it has these three properties, non-negative, permutation invariant, and additive. And you also exclude, and this is a more technical requirement, you exclude pathological functions that are not continuous. So if you also require some form of continuity, so mathematical niceness, then these three properties up to a multiplicative constant uniquely specify the Shannon entropy. So this is further evidence that the Shannon entropy is really the appropriate measure to quantify classical information. A last property that I would like to add to this inequality. I said the inequality is always valid no matter if there are correlations or not. This becomes an equality if and only if the random experiments are independent. I think one direction is clear. If the two random experiments are independent, then this should be an equality. But the converse is also true. Whenever you have a strict equality, then this means that the two random experiments must be independent. Next to the conditional entropy, one defines a further quantity that is very useful. That's called the mutual information of the two experiments A and B. That's defined as the difference between the ordinary entropy of B and the conditional entropy of B given the result of A. I already discussed the fact, and that's reflected in the inequality that we just saw, that the latter can only be smaller but not larger than the former. Yeah? So this difference is always non-negative. Yeah? So the mutual information defined in this way is non-negative. And this difference, this mutual information tells you something, or it quantifies how much the outcome of A already tells you in terms of information content about the outcome of B. Yeah? The larger this difference on the right-hand side, the more the outcome of experiment A already informs you, tells you about the outcome of experiment B. The way the mutual information is defined here does not look symmetric in A and B, but in fact it is. If you use the previous formula of the additivity, or the previous additivity property, and you solve that equation for the conditional entropy, you see the conditional entropy of B given A is the joint entropy of A and B minus the entropy of A. If you insert that below in the definition of the mutual information, then you find an alternative expression for the mutual information. That's the last line. It's the sum of the individual entropies of experiments A and B minus the joint entropy of the combined experiment AB. And written in this form, it's evident that the definition of the mutual information is symmetric in A and B. Once again, makes it plausible that it measures the correlation between the two experiments, because if they are uncorrelated, then you have the additivity, so the joint entropy is just the sum of the ordinary entropies, and this difference is zero. The mutual information is zero. But if they are correlated, then the ignorance about the combined experiment is smaller than the sum of the ignorances of the individual about the individual experiments. So this difference becomes positive, and you have a positive mutual information. Now we've encountered 3 different entropies, of 4 actually, so far. We had the ordinary entropy of relating to a single random experiment. We had the joint entropy relating to the combined experiment. We had the conditional entropy of one experiment given the outcome of the other. And we had at the end the mutual information. And the various relationships between these classical entropies can be nicely visualized in something like a Venn diagram. If you consider this first set or this first circle or ellipse to be the entropy associated with experiment A, and you have a second random experiment B, and with a second ellipse, and that represents the entropy of B, Then the combined area, if you wish, that is the joint entropy. And you see that whenever there's an overlap between the two ellipses, then the joint entropy is smaller than the sum of the individual entropies. And the difference, that's just the intersection, that's the mutual information. And on each side you have sort of a complement, which then are the respective conditional entropies. So on the left-hand side, that's the conditional entropy of A given the outcome of B. On the right-hand side, it's the conditional entropy of B given the outcome of A. And this little diagram nicely illustrates these relationships between the various classical entropies.